Hello friends, and welcome back to Survival Roots. If you're a homeowner tired of sky-high power bills, a builder who appreciates smart design, a DIY thinker who values practical materials, or simply someone who wants a cooler, healthier home without wasting money, this video is for you. Picture the middle of summer. The heat outside is relentless, the air feels heavy, and your AC unit is working overtime, roaring away while your electric meter spins faster than you'd like to admit. Then the bill arrives, and once again you're paying a small fortune just to make your own home livable. For years, we've been told this is normal. We've been taught that comfort has to come from machines, compressors, refrigerants, and constant dependence on the grid. But in real building science, that story is far from complete. What if one of the smartest cooling strategies ever developed wasn't modern at all? What if a simple structural feature, built into the house itself, could help lower indoor temperatures dramatically in peak summer, without fans, without motors, and without adding another monthly energy cost? That's exactly what we're diving into today. In this episode, we're looking at a remarkably effective idea that has been around for thousands of years, a passive cooling system that can turn the walls of a building into a natural engine for airflow. It can help remove stale air, reduce moisture problems, and cut the need for expensive mechanical cooling. Best of all, it does this with simple principles, practical materials, and logic any good builder can respect. So what is this system? How does it really work? And why did modern construction move so far away from ideas like this? Stay with me, because in this video, we're going to break down the science, the design, and the real-world value behind it. And before we get into it, make sure you subscribe to Survival Roots for more practical, cost-conscious building knowledge rooted in timeless design. The lost ancient genius. To understand why this idea still feels so disruptive today, we need to step back nearly 3,000 years to the dry, punishing heat of ancient Persia. Think about what it meant to build a livable city where summer temperatures could climb past 110 degrees Fahrenheit, all without electricity, compressors, or any kind of modern cooling equipment. What those builders had instead was something just as powerful: a deep understanding of heat, airflow, mass, and how buildings could work with nature instead of fighting it. That is where the bad gear, or wind catcher, comes in. These tall masonry towers were not decorative features. They were carefully designed climate control systems built from stone, mud brick, and geometry. In Yazd, a city that became famous for them, these towers still rise above the skyline as proof that passive cooling is not some new experiment. It is old, tested, and remarkably intelligent. And here is the part many people miss. Even when the wind is weak, these towers can still function through the stack effect alone. As the sun heats the tower, the air inside becomes lighter, rises, and escapes at the top. That upward movement creates suction below, pulling cooler air from underground water channels known as qanats into the rooms beneath. The result was so effective that Persian builders could help preserve ice in the middle of the desert using structures called yakhchals. Long before electric refrigeration, they were storing cold in extreme heat with nothing more than earth, mass, air movement, and smart design. And Persia was not alone. In ancient Egypt, early wind-catching forms appeared in elite residences. The Romans used underground channels to temper heat. Indigenous Americans built semi-subterranean dwellings that benefited from the Earth's stable temperature. Across time and across cultures, builders facing harsh climates kept arriving at the same conclusion. If you understand the sun, the ground, and thermal mass, You can move air and control comfort naturally. So that leads us to the real question. How can the same sun that overheats a building also become the force that cools it? The answer is a deceptively simple system known as the solar chimney. From a building perspective, the idea is elegant because it uses the most basic laws of physics and turns them into usable indoor comfort. You take a sun-facing wall, typically the south side in the northern hemisphere, or the equator-facing side more generally, and create a dark absorber surface. Then, you place glazing in front of it, leaving an air cavity between the two. Once sunlight passes through that outer layer, it heats the dark surface very quickly. The glazing helps trap that heat, much like a greenhouse. As the air in the cavity gets hotter, it becomes less dense, and that lighter air begins to rise. It moves upward through the shaft and exits through a vent at the top. The moment that happens, the system starts doing the real work. By exhausting hot air upward, the chimney creates negative pressure at the base, and that pressure difference begins drawing cooler replacement air into the building from shaded openings on the other side. This is not just a weak draft or a minor comfort boost. A properly designed solar chimney can move a surprising amount of air. In practical terms, that means stale indoor air is pushed out while cooler air is pulled in continuously and quietly. No fan motor, no humming equipment, no vibration through the wall, and no electrical draw every hour it runs. From a construction standpoint, that is what makes the concept so valuable. The building itself becomes the ventilation engine. And the most impressive part is that the system performs best exactly when the heat is worst. On the kind of afternoon when conventional cooling equipment is under peak strain and utility demand is highest, the solar chimney is strengthening its own airflow. The stronger the sun, the stronger the temperature difference, and the faster the air can move. In other words, the very condition that makes most homes depend more heavily on mechanical cooling is the same condition that makes this passive system work harder. The earth tube hack. Maximizing the chill. Now let's take the idea one step further, because this is where passive cooling becomes truly impressive. A solar chimney on its own can move air very effectively, but when you pair it with an earth tube, the whole system becomes far more powerful. Instead of simply pulling replacement air from a shaded opening, you guide that incoming air through the ground first, and let the earth do part of the cooling for you. One of the most useful things any builder learns is that just a few feet below the surface, ground temperatures stay far more stable than the air above. Even when summer heat is brutal, the soil below remains comparatively cool and steady. That means if incoming air is routed through a buried pipe before it enters the house, the ground can temper that air naturally along the way. By the time it reaches the interior, it can feel dramatically cooler than the outside air the house would normally be drawing in. That is what makes the combination so smart. The solar chimney becomes the driving force, creating the pressure difference that keeps the air moving. The earth tube becomes the temperature moderator, cooling that incoming air before it ever reaches the living space. Instead of relying on a compressor, refrigerant, or motorized fan, the system uses sunlight above grade and stable soil temperatures below grade to work together as one passive cooling strategy. From a building science standpoint, it is an elegant pairing. The chimney provides airflow, the earth provides thermal moderation, and together they can help maintain indoor comfort through severe summer conditions without ongoing electrical demand. Once you understand that relationship, the concept stops sounding experimental and starts sounding like what it really is: a practical use of materials, temperature, and pressure working exactly as nature intended. And at that point, the next question becomes impossible to ignore. If this approach is so logical and so effective, are there real modern buildings proving it at scale? Modern miracles. The proof is in the architecture. That is exactly where the modern evidence becomes so important. If solar chimneys and passive cooling were only found in ancient history, critics could dismiss them as outdated ideas that no longer fit modern buildings. But that argument falls apart the moment you look at the projects that are already standing and performing in the real world. Take the Eastgate Center in Harare, Zimbabwe. Completed in 1996 by architect Mick Pierce, this large commercial building became one of the most recognized examples of climate-responsive design. Pierce drew inspiration from termite mounds, which are famous for maintaining stable internal conditions despite major outdoor temperature swings. Instead of depending on conventional air conditioning, the building uses mass, ventilation, and carefully managed air movement to regulate heat far more naturally. Its heavy concrete structure absorbs cooler night air, and during the day, warm air is driven upward and out through a ventilation system built around passive principles. The results made the project impossible to ignore. Compared with similar conventionally cooled buildings, Eastgate used a fraction of the energy and avoided major construction costs associated with full mechanical air conditioning. That is not theory, that is performance. And it is not the only example. The Zion National Park Visitor Center in Utah also demonstrates how passive cooling strategies can reduce dependence on energy-intensive systems in a harsh climate. There, downdraft cooling towers and related passive design methods help cut energy use dramatically while delivering real comfort. These buildings matter because they prove a larger point. Passive cooling is not nostalgia, and it is not guesswork. It is measurable, publishable, buildable design. So, when we see thousands of years of successful climate-responsive construction and modern projects confirming the same principles, the real question becomes even sharper. If this knowledge has worked across continents, cultures, and centuries, how did so much of it disappear from mainstream Western construction in such a short time? The HVAC conspiracy. Why it's illegal. To understand how we got here, it helps to look at the moment mechanical cooling took over the modern world. In 1902, Willis Carrier developed a system to control humidity in a printing plant, and that breakthrough eventually reshaped architecture, comfort, and energy use everywhere. But it also helped create an industry built around equipment, servicing, replacement parts, and permanent dependence on powered systems. And that is where the contrast becomes impossible to ignore. A solar chimney is not a machine in the usual sense. It is made from durable building materials, glass, masonry, coating, structure. And once it is properly integrated, there is very little to maintain. No filters, no compressor, no refrigerant charge, no electronics waiting to fail. From a builder's perspective, it behaves less like an appliance and more like a permanent part of the house itself. That kind of solution does not fit neatly into a market built around recurring costs. Modern construction has largely been shaped by standardization, subcontracting, and quick installation cycles. It is often more profitable to build lightweight, underperforming structures and then solve the comfort problem later with mechanical equipment. Over time, passive cooling strategies were pushed to the margins, not necessarily because they failed, but because they stopped fitting the dominant business model and the dominant training system. By the late 20th century, passive cooling had become far less visible in mainstream architectural education, and many contractors were no longer exposed to it in a serious way. Then came the code problem. Building regulations tend to be written around familiar mechanical systems, while vertical shafts, ventilation paths, and unconventional passive designs often trigger extra scrutiny. Inspectors may require additional fire protection, dampers, or backup systems simply because the design sits outside the usual checklist. So even when the physics are sound, the bureaucracy can make the approach feel nearly impossible to adopt. And that is the irony. We are often told that compressor-based cooling is the advanced option, and passive design is old-fashioned. But in many cases, the opposite is closer to the truth. A machine forces a poorly designed building into comfort through energy use. A well-designed passive system achieves comfort by working with heat, air, and mass from the very beginning. That is not primitive, that is sophisticated building intelligence. 6. The Survival Roots Die Guide. But here is the part that matters most. No regulation, no sales pitch, and no industry trend can change the underlying physics. The sun still hits the same walls every day, and a well-designed building can still use that energy to move air for free. That is why this idea remains so powerful. It is not dependent on a brand, a utility company, or a maintenance contract. It depends on principles that are available to anyone willing to build more intelligently. So let's bring this down to a practical level. In general, there are two ways to think about a solar chimney: integrating it into a new build from the start, or adapting it as a retrofit on an existing home, workshop, or cabin. For many existing structures, the most realistic approach is an exterior chimney assembly built onto a sun-facing wall. The basic concept stays the same. A dark absorber surface collects heat, a transparent outer layer creates the air cavity, and the rising warm air generates the draft that helps ventilate the space. Material choice matters here. High-mass surfaces such as concrete, brick, or adobe can perform especially well because they do more than heat up quickly. They also store thermal energy and help keep the convection cycle stable. The outer glazing layer matters too. Budget-conscious builds may lean toward practical polycarbonate solutions, while higher-end installations can justify better-performing glass assemblies. The gap, the height, and the overall proportion of the chimney all influence how strong the draft becomes, which is why thoughtful design matters more than gimmicks. And one of the most appealing aspects of the system is that it does not have to serve only one season. In hot weather, it helps exhaust warm indoor air and support the flow of cooler replacement air. In colder months, the same sun-facing thermal mass can contribute useful heat when the system is configured to direct warmth inward instead of venting it away. That kind of dual-purpose value is exactly what good building design should deliver. Simple materials doing more than one job, with lower long-term cost and greater resilience. And that brings us back to the bigger picture. The solar chimney is not just an old construction trick. It is a 3,000-year-old answer to a problem that modern homes still struggle with every summer. It reminds us that comfort does not always have to come from noise, machinery, and bigger utility bills. Sometimes the smartest solution is the one that works quietly in the background, built into the structure itself. For too long, people have been taught to hand over comfort entirely to equipment, contractors, and power-hungry systems. But true resilience begins when we understand how buildings can respond to climate naturally. When we use thermal mass, airflow, orientation, and solar gain intelligently, a house stops being a sealed box that needs constant rescue. It starts becoming a system that works with nature instead of against it. That is what Survival Roots is really about, recovering practical knowledge that should never have been forgotten, and applying it in ways that make homes healthier, smarter, and more affordable to live in. So if you believe better building starts with timeless principles, solid materials, and clear thinking, make sure you subscribe to the channel and share this video with someone who is tired of expensive energy bills and fragile systems. And tell me in the comments, would you consider adding a passive cooling feature like this to your own property? And what other overlooked building ideas should we explore next? The sun has been doing this work all along. It is time we started designing with it again. Until next time, stay grounded, stay resilient, and keep growing your survival roots.